Welcome to Mrs. Lee's Chemistry Academy, where no students are left behind. Today we're going to talk about ideal gas law and gas stoichiometry. Now this is tied to the learning objectives from College Board, LO 2.6, that a student can apply mathematical relationships or estimation to determine variables for ideal gases. LO 3.4, the student is able to relate mass or volume or pressure to identify stoichiometric relationship in a reaction, including those involving limiting reactants. Let's first define what is molar volume at STP. Standard temperature and pressure means at 0 degrees C or 273 Kelvin and 1 atmospheric pressure, that 1 mole of any ideal gas occupies a volume of 22.4 liters. Practice problem number 1. At standard temperature and pressure, 0.280 liter of a diatomic gas weighs 0.475 grams. Calculate the molar mass of the gas and identify it. As we know, 1 mole of an ideal gas occupies a volume of 22.4 liters. We can then convert this 0.280 liter to the moles of 0.0125 moles. As molar mass is defined as mass over mole, we can take the 0.475 grams divided by 0.0125 mole, and we have a molar mass of 38 grams per mole. And that will fit with fluorine gas from the periodic table being diatomic molecule. Now let me show you how to derive ideal gas law. As we examine Boyle's law relationship, says pressure and volume are inversely proportional, and in the Charles law relationship, volume and temperature are directly proportional, and Avogadro's law that volume and moles are directly proportional. Now we can combine all these three relationships into one overall, that P times V over N times T is equal to a constant, which we call the ideal gas constant, R. Now when we cross multiply, we have PV is equal to nRT, and that's the ideal gas law, which I call, and some teachers call, Pivnert. And R is the ideal gas constant. Now R can take on different values depending on what unit of pressure we're working with. If we're working with unit of atmospheric pressure, then R is equal to 0.08206 liter atmosphere per mole dot Kelvin, assuming STP conditions. If we use millimeter mercury, then we obtain a value of 62.4 mmHg dot liter per mole dot K. And if we use 101.325 kilopascal, we end up with 8.314 kPa dot liter per mole dot K. So when you work on problems, it's really important for you to choose the right value of R to use based on the unit of pressure in the problem given. Practice problem number 2. Airbags in automobiles are inflated upon impact that triggers the following reaction of sodium azide. That sodium azide is decomposed in sodium and nitrogen, and the nitrogen will fill up the bag. Let's say we need a volume of 12 liters to fill up the bag at STP conditions. How much of the NaN3 do we need to begin with? So we take the 12 liter of nitrogen using 22.4 liter per mole converted into 0.536 moles of nitrogen. Now, then we relate that to the mole relationship between 2 moles of NaN3 and 3 moles of nitrogen, and using the molar mass of NaN3, we obtain 23.2 grams of NaN3. Practice problem number 3. Here I have a reaction between iron 3 oxide and carbon monoxide to form iron and carbon dioxide. Given a certain mass of iron 3 oxide and certain volume and pressure and temperature of carbon monoxide gas, find out how many moles are given, which one is limiting reactant, and what's the mass of iron formed. And the percent yield if we only get 13.5 grams of iron. First, we calculate the moles of carbon monoxide given using ideal gas law PV over RT. We obtained 1.03 moles of carbon monoxide. Now we calculate moles of iron 3 oxide given based on 22.484 grams. We get 0.143 moles of iron 3 oxide. Now we take this moles of carbon monoxide 1.03, convert into moles of iron, 0.687 moles of iron. And if we use 0.143 moles of iron 3 oxide using a mole ratio of 2 to 1, we then calculate to be 0.286 moles of iron. Because the iron 3 oxide yields lesser number of moles of iron, therefore, it is the limiting reactant. And using that 0.286 moles of iron, we convert it into 16 grams of iron. And now we do a percent yield of 13.5 over 16. We get 84.4% yield. Practice problem number 4, my favorite. Here we have an unknown hydrocarbon gas, CxHy, and it's burned with 3.17 grams of oxygen, forming carbon dioxide and water vapor in a 1-liter flask at 127 degrees C. After the reaction, the partial pressures of CO2 and water are found to be 2 and 2.5 atm respectively. Now calculate the pressure of oxygen given before the combustion and deduce the formula for the unknown hydrocarbon and write a balanced equation for the combustion reaction. So first we convert the 3.17 grams of oxygen into 0.0991 moles, and then we use the ideal gas law to find the partial pressure of oxygen given at the beginning, which is 3.25 atm of oxygen. Now we do a pressure ratio between oxygen and carbon dioxide and water. So it's 3.25 to 2 to 2.5. And then I multiply that by an integer of 2 because I will try to convert it into whole numbers if I can. So the pressure ratio is 6.5 to 4 to 5. Now because we know the pressure is directly proportional to number of moles, the pressure ratio can be considered as mole ratio in the balanced equation. So now we substitute the mole ratio into the balanced equation, and you have CxHy and 6.5 moles of oxygen to yield 4 moles of carbon dioxide and 5 moles of water. Now because I want to get rid of this, I want to turn it into whole numbers, see what I'm going to do next. Alright, my X is 4 moles of carbon, and my Y is 5 times 2 or 10 moles of hydrogen. Therefore, the formula of the unknown hydrocarbon is C4H10, and this is butane. Now, going back to the original equation, because I want to turn them into whole numbers, I multiply everything by 2. And hence, I obtained 2 moles of butane burned with 13 moles of oxygen to yield 8 moles of carbon dioxide and 10 moles of water. To sum up the lesson that we have learned today, 1, we learned the definition of molar volume as standard temperature and pressure, that is 0 degrees C and 1 atmospheric pressure, occupying a volume of 22.4 liter for 1 mole of any ideal gas. Secondly, we learned how to derive the ideal gas law, PV is equal to nRT. And lastly, we applied the ideal gas law mathematically to solve problems in gas stoichiometry. I hope that you have found the above lesson to be helpful to you. I welcome any comments from you, and I do hope to see you again next time.